All right, welcome back. Dr. P here, and in this lecture we'll take a look at the chemistry of nitriles, that is, ways of preparing nitriles and reactions of nitriles. First of all, what is a nitrile? Well, nitriles contain what we think of as a cyano group, what is called the cyano group, which is a C triple bond N. Now, I should note here that this is a very polar bond. Okay, just like a C double bond O is very polar, C triple bond N is also polar. And so we end up with a partial negative charge at the nitrogen and a partial positive charge at the carbon. So that's going to affect how these nitriles react. And like I said in the last video, we do consider nitriles to be a type of carboxylic acid derivative. All right. So let's look at some methods of preparing nitriles. Okay, what have we seen so far? Well, we've seen that we can use cyanide as a nucleophile. And we've seen this in two ways. Last semester we saw using cyanide in an SN2 reaction. So let's say we had R CH2Br. We have a primary alkyl halide. Maybe it'll work with secondary. And we can treat this with NaCN and acetone. We'll get R CH2C triple bond N. We can also use carbonyls. And when I say carbonyls, I mean aldehydes and ketones. In this case, we will have our carbonyl compound here, and we'll go ahead and treat this with NaCN, followed by quenching with acid, and this gives us now a cyanohydrin. Okay, and I did mention that in chapter 19. I know it was a little quickly, but I did mention it. It is in there. We could use NaCN and HCN as another reagent, so just one step. You may see that in some texts. I think the practice problem set may have that. The text that I got that from use that reagent. But really it's the CN minus ion and then some kind of acid to protonate our oxygen at the end to make the cyanohydrin. All right. Now another method is to prepare nitriles from amides using SOCl2, thionyl chloride. So if I have R, C to bond O, NH2, and I treat that with SOCl2, I'll get R, C triple bond N. And if you're really interested, you can take a look at the mechanism in the text. But I will say that I'm not going to hold you responsible for this mechanism, so if you don't want to look at it, you don't have to. All right. So these are a few ways to prepare nitriles, but it turns out they undergo quite a variety of reactions. So let's take a look. All right, let's take a look at some reactions of nitriles. All right. So, like before, remember we've got our polar bond here with a delta minus and a delta plus. So we could have some nucleophile, so let's call that nuc minus, add in, and that will go ahead and give us now some kind of funky intermediate. And this is called an imine ion intermediate. And then that could react further to give us products. So it may grab a proton or something, etc., etc. So what can we do? Well, let's see. So let's take RC triple bond N. Now, one thing we could do is we could actually hydrolyze this using H3O plus or H2O, OH minus, so NaOH. And we could get an amide, which then further reaction will take us all the way to a carboxylic acid. Generally, this requires heat. It requires a long, quite a bit of time, but it can happen. We'll actually go over the mechanism for that. We could use a hydride donor as our nucleophile, and like lithium aluminum hydride, and that will give us R, C, H, H, and H2. We get an amine. And then another nucleophile we could use would be the Grignard. Use R prime, MgBr, and then we'll quench with water. And what happens is one Grignard adds, and then we get, so this would be our R prime here. No more Grignards will add because we've got this N minus. We can't push more, then we'd have an N2 minus, that's just crazy talk. So because we have a negative charge on that nitrogen, this bond is not as polar as it was before, so carbon's not as electrophilic. The Grignard won't add, so we only get one Grignard adding. And then when this intermediate reacts with water, the water converts this into because it's kind of like an imine, it converts it into an aldehyde or ketone. Or a ketone, I guess, in this case. The water also quenches the Grignard, so we don't have to worry about the Grignard reacting with the ketone that we just made. So I don't know, I always thought that was kind of cool. It's like, yeah, you react your nitrile with the Grignard and you get a ketone? Sure, why not? All right. So those are some reactions of nitriles. There's two more things that I did want to show you guys. And one is, let's look at the following. Let's say we had this. Maybe we'll do this. You need to make an alpha hydroxy acid? What's an alpha hydroxy acid? Well, remember our alpha carbon is the next one over from the carboxyl group. So if we have a hydroxyl group there, an OH, that's an alpha hydroxy acid. You may have heard of these in skincare, for example. So what we can do is we can actually make use of what C triple bond N does. So we're going to use a nitrile. Actually, a cyanohydrin. but it makes use of the nitrile, the chemistry of the nitrile. So let's go ahead and take our RC double bond O R prime, and we'll treat that with NaCN followed by H2O, and that gives us now RCOH R prime C triple bond N. Now hydrolyze. H3O plus and heat. And what do I get? I get RCOH R prime. Those stay the same, but now my nitrile gets hydrolyzed to a carboxylic acid. Okay, it's hydrolyzed, hydrolyzed all the way to the carboxylic acid. So I now have C double bond O OH. There we go. Here's my carboxylic acid, my alpha hydroxy carboxylic acid. I don't know, I always thought that was kind of a cool reaction. It's an interesting way to introduce an alpha hydroxy group to something. Okay, let's see here. The last thing I want to do is actually go over the acid-catalyzed hydrolysis of nitriles. That is the mechanism. So, acid-catalyzed hydrolysis of nitriles mechanism. I used to make students, I know last year I made students do this on an exam, but it just takes a while, so I'm going to walk you through it. And there'll be plenty of other mechanisms for you to do on an exam. So acid-catalyzed means we've got acid-catalyzed hydrolysis means we have H3O+. We have protons, we have water, we have aqueous protons. So we can start with our RC triple bond N, and the first thing we should do, of course, is protonate, because we don't have a strong nucleophile, we just have water. So the text shows some of the base catalyzed hydrolysis of, or base promoted hydrolysis of nitriles. And it shows a little bit of that mechanism, so you can take a look at that if you want. But I wanted to go over the acid-catalyzed one with you guys. So now we've activated our nitrile, and that carbon is even more electrophilic, and so we can get nucleophilic attack by water on that carbon, and then we get electrons being pushed up onto the nitrogen, which now gives us RCOHH, lone pair, positive charge, double bond N, and let's put an H here, and a lone pair. So now we'll do a couple of proton transfers, and I could have a molecule of water deprotonate and a molecule of H3O+ that has a proton pulled off by that lone pair, but I'm just going to do the intramolecular one instead because, well, I'm feeling lazy. And that now gives us RC double bond N H positive charge OH lone pair. Now I can go ahead and push electrons and get, and I'm gonna like flip this guy over, so I'm gonna get RC double bond OH positive charge, and then NHH. I can get one more deprotonation, and that now leads me to leads me to a amide. All right. Now, this could react further. So if I had my H3O plus here, of course, I could undo that deprotonation. So I'll reprotonate here. I know, I'm just doing the reverse. I'm going back to here, but I figured it was easier to write it out this way. Positive charge, NHH. Now, because I have my activated carboxyl here, I can have water come in as the nucleophile. Electrons being pushed up there, and that is now going to give me RCOH, lone pair, NHH, lone pair, OH, lone pair, positive charge. Let me scoot that back in frame. Now I will do my lazy intramolecular proton transfer. And that gives me now protonated nitrogen species. Let me move that up a little. There we go. Try to keep everything on the page here, or in frame here. Now I can lose my leaving group, RC double bond O, H lone pair, positive charge, OH, and I've got NH3, and now I can go ahead and actually my NH3 that I made is actually a pretty good base, so you could have water do it if you would rather, but my NH3 will go ahead and pull that guy off. And I'll get RC double bond O, OH. There we go. So I think this is 10 steps. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 steps. Now, of course, the two of those are making the amide and then reprotonating. So you could just go straight from this step to adding the water as a nucleophile to that guy and jump there. But I did want to show the intermediate formation of the amide. Amides are pretty stable. So you can do an initial hydrolysis and get an amide. And then you have to do more hydrolysis to go all the way to the carboxylic acid. One of the reasons I'm not assigning this, like we're not going to put it on a quiz or an exam, is because it's a little repetitive. What do I mean by that? Well, we're doing a bunch of the same thing over and over again. We have proton transfer, nucleophilic attack, proton transfer, rearrangement of electrons, proton transfer, nucleophilic attack, proton transfer, loss of leaving group, and proton transfer. So we're transferring a lot of protons. We've got a couple of nucleophilic attacks. We have loss of a leaving group. And there's just a bunch of steps that, I don't want you to feel like, you have to be able to do this like on a quiz, because this could take a little while. Anyway, but I did want to show it to you. All right, so that is it for chemistry of nitriles. We'll be moving on to the chemistry of carboxylic acid derivatives in chapter 21 next. All right. So until next time, stay safe out there. Bye now.